Hello my dear students. So in my last class I was explaining about the significance of wave function, that is psi and psi square, and postulates of quantum mechanics. So mainly we saw 5 postulates. So each explained the physical state of the system, the wave function and its first and second derivatives, and what are the possible values of any physical quantity of a system like energy, angular momentum, and the expected average value, so which was observable as A, and what does it corresponds to in terms of an operator. And the fifth postulate, so for every system, so the time dependent Schrodinger equation exists, which is given by a certain mathematical expression. So these are the 5 different postulates of quantum mechanics, and this is where we stopped in our previous class. And in this session, let us understand Schrodinger wave equation for particle in one-dimensional box. So this is very important equation in quantum mechanics. So little bit complicated to understand at the beginning, but if we clearly know the concept, so then it is easier for us to understand this Schrodinger wave equation for particle in one-dimensional box. So now, so this is the figure which represents the particle in one-dimensional box. So consider a particle, okay, so it is having a mass of m. Let me call the mass of a particle as m, which is restricted to move in a one-dimensional box of length a. Okay, so it is having a length a. So this is the length which I have represented, and it is restricted to move in one-dimensional. Say for example, if it is moving like this, so this is the x-axis. So this particle has been restricted to move only in the x-axis, okay, and it is having infinite high walls. So here, if we measure the potential energy of this particle which is restricted inside this, so these two are the boundaries, okay, so these two are the boundaries, and here the potential energy of the particle will be equal to 0, whereas in the outside, so the potential energy might be up to infinite, okay. So in an atom, the motion of an electron which is restricted to move within a small distance of length a, okay, so this is a small distance of length a in the direction, that is, as I said, in x direction, it can be compared with the motion of the particle in a one-dimensional box. For the sake of simplicity, so it is assumed that the potential energy of the particle is 0. Okay, so here the potential energy of the particle is considered as 0 everywhere inside the box, that is, so Vx will be equal to 0. Thus, inside the box, the Schrodinger equation in x direction is written as, so this is how we are going to represent the Schrodinger wave equation in the x direction. Okay, so that is so del square psi divided by dx square plus 8 pi square m divided by h square into e minus v psi into x, which is equals to 0, and let this equation be named as equation number 1. For the particle within the box, okay, so suppose if the particle is within the box, then as I said, the potential energy V is equals to 0. Therefore, the Schrodinger equation takes the form, so del square psi divided by dx square plus 8 pi square m divided by h square into, so here V has become 0, V is equals to 0, so that is why the whole term is removed, and what left is E into psi into x, which is equals to 0. Okay, so this is when, so this is when a particle is within the box and which is having the potential energy of 0. Okay, so and this equation is called as equation number 2. So I can simplify this equation, that is, so I can represent this term, that is 8 pi square m divided by h square into E as k square, and okay, so and this k square is a constant and independent of variable x. So here k square is a constant and it is constant independent of variable x. and let me call this equation as equation number 3. So this equation number 3 is a second order differential equation which has a solution of the form. So psi is equals to a sin kx plus b cos kx. Okay, so this is in the differential equation form. Which one? So this equation number 3. So this equation number 3 is a second order differential equation and it has a solution of the form psi is equals to a sin kx plus b cos kx, and let me call this equation as equation number 4. Here a and b are considered as constants. Okay, so here in this a and b are constants. Suppose so in this figure itself we will understand the boundary conditions. So here in this boundary, so let me call these two as boundaries, and here the potential energy will be equal to 0 and the particle is moving in a x direction. So therefore here it will have a movement which will be considered as x is equals to 0 and this is x is equals to a, whereas so in the outside the boundary, so what happens is so v is equals to infinite. There is a chance of infinite probability of finding that particular particle. Okay, so here when the particle is within the boundary, so there is a probability of finding that in the restricted boundary, so within this boundary itself that particle has to be present. And one more condition is that particle, it has got one dimension, that is it can move towards x axis, that is x direction, whereas when the particle comes out of this boundary, so there is a probability of finding that particle anywhere. So that is why we call it as so v is equals to infinite. Okay, so depending upon the values of a, b and k and psi, so we can have many values, but the acceptable values of psi should satisfy the boundary conditions. Okay, so what are the boundary conditions? So boundary conditions are psi should be equal to 0 at x is equals to 0 and x is equals to a. Okay, so now let us put psi is equals to 0 at x is equals to 0. Then what happens? Equation 4 becomes okay, so go back to this equation. So substitute the value of psi is equals to 0 at x is equals to 0. Then 0 is equals to b sin 0 plus b cos 0. It becomes like this. So what upon simplification we are going to get? 0 is equals to 0 plus b, otherwise we can write it as b is equals to 0. Okay, so thus when x is equals to 0, equation 4 becomes psi is equals to a sin kx, and let me call this equation as equation number 5. So one more condition we can have, that is suppose if psi is equals to 0 when x is equals to a, then equation 5 becomes so 0 is equals to a sin ka, and let me call this equation as equation number 6. So this equation, that is equation number 6, so this equation holds good only when the value of ka are integral multiples of pi, that is ka is equals to n pi. So where n is an integer. Okay, so here n might be an integer, that means 1 2 3 4 5 like that. Suppose if n is an integer, then only so this equation, that is 0 is equals to a sin ka, holds good. Okay, now substitute the value of n, that is substituting equation 8, so this value, equation 8 value in equation 5, what we are going to get? If we substitute the value, so upon substitution we are going to get psi is equals to a sin into n pi divided by a into x, and let me call this equation as equation number 9. And this expression or this equation, that is equation number 9, so this gives the expression for the eigenfunction psi. So psi has been defined now. Psi is equals to a sin into n pi divided by a into x. Okay, so the expression for the eigenvalue of the energy may be obtained from equation number 3. So if we go back and see the equation number 3, so then substitute this value, that is equation number 9 value. So we are going to get E is equals to k square h square divided by 8 pi square m. Okay, substituting this value of k from equation 8, we are going to get E is equals to n pi divided by a to the whole square into h square divided by 8 pi square m. Okay, and we can also simplify this or we can write it as E is equals to n square h square divided by 8 ma square, and let me call that equation as equation number 11. So where n is called a quantum number and it takes the values like 1, 2, 3 and never be 0 or fractional. Okay, so equation 11 is the expression for energy of the particle in a one-dimensional box. Okay, so this is what we are going to understand by looking to the Schrodinger wave equation in one-dimensional box. So what are the observations made from the study of particle in the box? Expression for energy of the particle in one-dimensional box given as so E is equals to n square h square divided by 8 ma square, where m is the mass of the particle and a is the width of the box. Okay, so this is what we are going to get by observing the Schrodinger wave equation for a particle in a one-dimensional box. And next is a quantization of energy. Since n can have only integral values which is equal to 1, 2, 3, 4, 5, etc., from the equation it follows that, okay, so from this equation which we have deduced based on the Schrodinger wave equation in a particle which is in a one-dimensional box, so we can have the energy which is associated with the motion of a particle in a box can have discrete values. That is, the energy is quantized. So here each the particle which is there, which is located in the one-dimensional box, so it is quantized. The integer n is called as quantum number of the particle. Now putting n is equals to 1 or 2, 3, 4, 5, so we have or we can get the discrete energy levels of the particle of mass m confined in the box of length a, which is shown in the figure. Okay, suppose if n value, that is integer value, is 1, so then we will have E1 is equals to suppose if n is equals to 1, then E1 is equals to h square divided by 8 ma square. Suppose if the integer value n is equals to 2, then it is E2 which is equals to 4h square divided by 8 ma square. Suppose n is equals to 3, then E3 9h square divided by 8 ma square. Okay, so all these energy levels, that is the discrete energy levels of a particle of mass m which is confined in a box of a width a, so it is deduced or calculated with the help of this equation. E is equals to h square divided by 8 ma square. So this holds good only when n is equals to 1. Okay, suppose if n is equals to 2, so then it is going to take, so 2 square, so that means 4, 2 square means 4, that is 4h square divided by 8 ma square. So with the help of this expression for energy of the particle in one-dimensional box, we are going to calculate various different discrete energy levels of a particle. Okay, so the minimum energy which is possessed by the particle is not 0, but it has a definite value which is called as a 0 point energy. So we call it as 0 point energy. So there we find the existence of 0 point energy. That means so for n is equals to 1, energy equation reduces to E is equals to h square divided by 8 ma square. So this implies that the minimum energy possessed by the particle is not 0, but it has definite value which is called as 0 point energy. Okay, so with the help of this, so we can solve a problem which is a simple problem where they have asked to to calculate the ground state energy for an electron which is confined to a potential well having a width of 0.2 nanometer. So if you look on to the solution, here the energy for a particle in one dimensional box is given by E is equals to n square h square divided by 8ma square. So what and all the informations they have given? So they have asked that the ground state energy, so that is why, so n must be equal to 1, and the width, A is the width, A is equals to 0.2 nanometer, that means 0.2 into 10 raised to minus 9 meters. And this is Planck's constant, and next is the mass of the electron. Okay, so we have the mass of electron. So for a electron, the mass will be equals to m is equals to 9.11 into 10 raised to 31. Okay, and substitute all the values here. So we know n, what is n? 1. H is Planck's constant, m is mass of the electron, and a is a square, it is a width. Okay, so the width of a potential well, that is 0.2 nanometer. Substitute all the values, so we are going to get 1.506 into 10 raised to minus 18 joules. Suppose if it is for 1 mole of electrons, then the energy will be equal to, so E is equals to, so 1.506 into 10 raised to minus 18 into 1 mole means, so this is Avogadro's number. So using that Avogadro's number, so we are going to calculate for 1 mole of electrons what will be the energy at the ground state, that is ground state energy for an electron which is confined to a potential well having a width of 0.2 nanometer. Okay, so in this way, so we can calculate the ground state energy as well as the next ionization energies for an electron which is confined to a potential well can be calculated with the help of this Schrodinger wave equation for particle in one dimensional box. Okay, so I am going to stop it here. So in my next class we will understand about Schrodinger wave equation for hydrogen atom. Thank you, dear students.